Welcome to the fourth session of Functions and Relations series. In this session, we are going to consolidate and level up what we have learned previously, including composite function, inverse function, and relations between sets. We will demonstrate more analytical approach through solving 5 worked examples. Hello, Math Champions! I'm Dr. Chen. If you want to improve your math skills and understanding so that you gain confidence, enjoy math more, and get better results, click subscribe and hit the notification button so that you don't miss anything. Welcome to the fourth session of this Functions and Relations series. Through this session, we will introduce the concepts of composite functions and inverse functions, as well as how to find their implied domain and range by going through 5 worked examples. Composition of 2 functions occur when the output of one function becomes the input for a second function. As shown in the diagram, the composite function g of fx involves expressing gx in terms of fx. On the other hand, the composite function f of gx involves expressing fx in terms of gx. The domain of the composite function g of fx equals the domain of fx, while the domain of the composite function f of gx equals the domain of gx. When 2 functions are composed, the output of the inner function becomes the input for the outer function. This means that if the composition is possible, the range of the inner function must be a subset of the domain of the outer function. Sometimes it may be necessary to restrict the domain of the inner function to ensure that its range lies completely within the domain of the outer function. The domain of the inner function is always the domain of the composite function. As for inverse relations, the inverse is obtained by interchanging the x and y coordinates. In the meantime, domains and range are also interchanged between a pair of inverse relations. However, as we know, the inverse produced are not always functions. Any relation that is many to one will have an inverse that is one to many, and hence this inverse will not be a function. Only one-to-one functions will have an inverse that is also a function. In some cases, the inverse process involves restricting the domain of the original function so that the inverse is a function. Example 1 shows 2 sets A and B, where in set A the rule is fx equals x, while in set B the rule is f of x minus 1 equals x plus 1. Here fx is a quadratic function which equals x squared plus bx plus c. Set A contains only one element, which is 2, and the question is to find all the elements in set B. In order to find the elements in set B, we first need to calculate the linear coefficient b as well as the constant c in the quadratic function fx. Since there is only one element in set A, the quadratic equation in set A has repeated roots, so its discriminant must be equal to 0. Now we have b minus 1, or in parentheses squared, minus 4c equals 0. And because 2 is the repeated root, it can be substituted to the quadratic equation, and hence we have 4 plus 2 times b minus 1, or in parentheses plus c equals 0. Solving the simultaneous equations by the substitution method, we obtain b equals -3, c equals 4, so the quadratic function becomes fx equals x squared minus 3x plus 4. The next step is to find the root in set B. Since the variable in set B is x minus 1, therefore f of x minus 1 equals x minus 1, or in parentheses squared, minus 3 times x minus 1 plus 4, which equals x plus 1. After simplifying the equation, we have x squared minus 6x plus 7 equals 0. Since the discriminant of the quadratic equation is greater than 0, we may apply the quadratic formula method to obtain the roots of this equation. Hence, the elements in set B are the two roots of this quadratic equation, which are 3 minus square root 2 and 3 plus square root 2. Example 2 has two sets A and B. In set A, all the real elements satisfy an inequality of x squared minus 2x minus 24 less than 0, while in set B, all the real elements satisfy an inequality of x squared minus 4a plus 3a squared, where a is the parameter. The question is to find the real value range of a, given that the first one, if the intersection between sets A and B is null, and the second question is if set B is a proper subset of set A. The first step we do is to solve the inequality of set A by factorizing of x squared minus 2x minus 24. After solving the inequality, all the elements in set A are real numbers, and they are between -4 and 6. The second step is to solve the inequality of set B, where A will be its parameter. Factorizing the inequality, and it becomes x minus a, or in parentheses times x minus 3a, or in parentheses less than 0. To answer these two questions, we need to discuss the value range of a when it is greater or less than 0. When a is greater than 0, the elements in set B is from a to 3a. In order to make the intersection of sets A and B is a null set, here a must be greater than or equal to 6. When a is less than 0, the elements in set B is from 3a to a. Therefore, in order to make the intersection of sets A and B is a null set, here a must be less than or equal to -4. In summary, when a is less than or equal to -4 or greater than or equal to 6, there is no intersection between sets A and B. Here we continue work on question 2 of example 2. Now we start to discuss the value range of A in order to find out under what circumstances set B will be a proper subset of set A. When A is greater than 0, since set B is a proper subset of set A, 3a must be less than or equal to 6. Therefore, the value range of A under this condition is greater than 0, and at the same time A is less than or equal to 0. When A is less than 0, since set B is a proper subset of set A, 3a in this case must be greater than or equal to -4. Hence, the value range of A is greater than or equal to -4 over 3, and at the same time A is less than 0. When A equals 0, obviously, in this case, set B is a null set, which is also a proper subset of set A. Now, in summary, when a is between -4/3 and 2, including both endpoints. Set B is a proper subset of set A. Example 3 is based on the function fx, which equals 1/x², where the domain of x is defined as positive real number. There are two questions follow, and the first one is to find the composite function f of fx. The second question is to evaluate its inverse when x equals 16. As for the first question, since gx is a composite function f of fx, here the output of fx is an input of fx. So gx equals x to the fourth. Since gx equals x to the fourth, its inverse function equals the fourth root of x. Hence, the inverse function of gx equals 2 at x equals 16. Example 4 is the circular function of cosine 2x/3 equals square root 3 multiplies sine 2x/3, where the domain is between -3π/2 and 3π/2, including both endpoints. Since the equation can be transformed to tangent 2x/3 equals 1/square root 3, we may use the inverse tangent or arctangent function to solve this equation. Hence, we have 2x/3 equals nπ plus arctangent 1/square root 3. Here n is an integer. You may recall the value of arctangent 1/square root 3, which equals π/6. After rearrangement, x is expressed as 3nπ/2 plus π/4. Then, according to the given domain, we choose the appropriate n values to work out all the possible x values. Therefore, when n equals -1, x equals -5π/6. When n equals 0, x equals π/4. In summary, x sub 1 equals -5π/6 and x sub 2 equals π/4. Example 5 presents a quadratic function with the parameter a contained in its quadratic and linear coefficients. The question is to ask about the value of a given that the quadratic function has a maximum value of 3 over the domain between -3/2 and 2, including endpoints. To answer this question, we need to transform the expression of the function to its turning point form. Since the quadratic coefficient is a, we may move it out so that we can add a constant term to make it a complete square. After being simplified, the turning point form is presented here. Since the maximum value lies over its domain between -3/2 and 2, including endpoints, the maximum value can only be obtained at the turning point or at the either endpoint of the domain. Here we continue work on question 2 of example 5. Since the maximum value can only be obtained at the turning point or either of the two endpoints of the domain, we here discuss all the scenarios accordingly. First, we assume that the maximum value of 3 is obtained when x is at the turning point of the quadratics, which is 1 minus 2a/2a. Hence, the y-coordinate of the turning point is expressed by the result of 8a minus a squared minus 1/4a, which equals 3. We solve this equation and find a equals -half. Substituting the calculated value of a to the quadratic turning point form, we have fx equals half times x plus 2 all in parentheses squared plus 3. If we substitute one of the endpoints x equals to 2, for example, into the question and find that f2 equals 11, which is greater than 3, So a equals negative half is not the solution we need. Now let's look at one of the endpoints of negative 3 over 2. After substituting the x value by negative 3 over 2 to the quadratic function, we calculate the value of a, which equals negative 2 over 3. Then this value of a is back substituted into the quadratics, and it becomes fx equals negative 2 over 3 times x squared minus 7 over 3 times x plus 1. Then the turning point form of this fx becomes negative 2 over 3 times x plus 7 over 4, or in parentheses squared, plus 73 over 24. As it can be seen, in this case, the x-coordinate of the turning point is on the left side of the given domain. Therefore, over the given domain, this quadratic is a strictly decreasing function, and its maximum value is at its lower end point. Therefore, a equals negative 2 over 3 is a solution we need. Here we continue work on example 5. Now let's take a look at the situation of the other endpoint. When x equals 2, we calculate the value of a, which equals half. After taking the calculated a value, the function fx equals half x squared plus 1. Obviously, the maximum value of this quadratic function is 3 at the point of x equals 2. So a equals half is the solution we want. In summary, the value of a satisfying the requirement are negative 2 over 3 and half. If you enjoyed this video, please give it a thumbs up and subscribe to help me make more math content like this. I will see you in the next video.